Okay, AP Chem, we're continuing on with day 32, lesson 16. We're going to do our second gas stoichiometry problem. All right, so first question is how many liters of H2O? So we're going to go up to H2O over here, and liters is up here. That's a question mark. Can be formed by 4.29 grams of lithium hydroxide, LiH. So 4.29 is down here. All right, so the path is we need to get up inside the dashed line here into the equation. So we use our molar mass for lithium hydroxide. So I've given those to you here. Normally you just compute those off the periodic table. Get into moles of lithium hydroxide, come across the moles of water, and then come out into liters of water vapor using the 1 mole equals 22.4 liters. Again, everything we're doing in this assignment is standard temperature pressure, so that relationship remains the same between moles and liters of a gas, of a vapor. Let's go ahead and set it up. Okay, so first conversion we have to make is using molar mass of lithium hydroxide, 1 mole for every 23.95 grams or 23.95 grams for every 1 mole. Which one do you want to have on the bottom? And you have to have grams of lithium hydroxide cancel, so the 23.95 is on the bottom. Grams lithium hydroxide cancels with grams. And now we're sitting in this box right here. We need to get over to water. So I'm going to go ahead and write coefficients here. First of all, I should check to see that everything's in balance. 2 Li, there's a hydrogen, 2 hydrogens, 2 oxygens, 2 oxygens, and 3 oxygens and 1 oxygen, so that's 4. And finally carbon is 1 and 1. So everything's in balance. Okay, so it is 1 mole of H2O for every 2 moles of lithium hydroxide. We need moles of lithium hydroxide right here to cancel, so we're going to put the 2 moles of lithium hydroxide on the bottom. And moles lithium hydroxide cancels. Now we need to come out of the equation. We're sitting in this box right here. We need to come out to here using this standard conversion for gas at STP. So it's going to be, we need moles of H2O on the bottom. So we're going to come here, it's going to be 1 mole H2O. Okay, there you go, moles H2O, moles H2O. All right, everything's set up. Last man standing is lithium, liter, of H2O. So 4.29 times 1 times 1 times 22.4 divided by 23.95 divided by 2. And that gives me 0.136, 3 significant figures, so I'm going to leave it at that. And there's your answer. That many liters of H2O. Okay. Let's keep going. Let's go ahead and just clean up our organizer here. And we want to, it's asking how many liters of CO2. So here, up here is liters of CO2 are required to completely react with 12.87 grams of LiOH. In a sense, this is like a limiting reactant problem. So we're down here with 12.87. Yeah, it's telling you what do you need to do in order to use up all of this. I mean, how much of this do you need to use up all of this? How much of this do you need to use up all of that? Okay, so let's get it everything. We need to get it into moles. So let's go ahead and set this up. And this is going to be again 3 conversions. You have to get into the equation LiOH, move over to carbon dioxide, moles to moles, and then move out up to liters of CO2. All right, move up a little bit here. Okay, first we need molar mass to get into the equation here for LiOH. So you got 1 mole over 23.95 or 23.95 over 1 mole. You need grams on the bottom here to cancel with grams of LiOH. So we're going to write it like this. Grams of LiOH cancels with grams of LiOH. Now we're sitting right here in the moles inside the equation. We need to move over to moles of CO2. Let's go ahead and put coefficients on these. So it's 2 to 1. We need moles of LiOH to cancel out. So it's 1 mole of CO2 on top and 2 moles of LiOH on the bottom. Moles of lithium hydroxide, moles of lithium hydroxide. So now we're sitting in this box. Now we need to use this conversion moles to liters to get out. We need moles of CO2 on the bottom. And liters of CO2 is going to go on the top. Mole CO2 cancels and cancels. Liter CO2 is the last one standing there. So now we're ready to go ahead and do the calculation. And that's going to be 12.87 times 1 times 1 times 22.4 divided by 23.95 divided by 2 divided by 1, and that's going to equal 6.02. And I've got 3 sig figs right there with 22.4, so I'm going to stick with that, 6.02. Okay, next question. Try to keep everything on here as best we can. How many grams of excuse me, lithium carbonate are formed from 14.01 grams of lithium hydroxide? So we go over here to lithium carbonate and it's looking for grams to grams. This is something we would have done last week with grams to grams. And it's 14.01. Okay, so the path is we've got to go into the equation, come across moles to moles, and come back out of the equation in that direction. So go ahead and set that up. Okay, there we have that set up. All right, so we need to go in from grams into moles. There's the molar mass, 1 mole of LiOH for every 23.95 grams of LiOH, or 23.95 over 1 mole. We need grams of LiOH on the bottom to cancel out, so we're going to put 1 mole on the top. Okay, grams of lithium hydroxide cancels and cancels. Now we have moles of LiOH, so we're sitting in this box right here. We need to get over to moles of lithium carbonate. So it's a 2 to 1 relationship. So we need moles of lithium hydroxide to cancel out. So we're going to put the lithium carbonate on the top. And we're going to put the moles of lithium hydroxide, there's 2 of those, on the bottom. Moles of lithium hydroxide cancels there and there. Finally, we have to come out of the equation. So molar mass is 1 mole of lithium carbonate for every 73.89 grams. We need moles of lithium carbonate to cancel, so we need it on the bottom here. And we need the grams up on the top. Okay, and moles of lithium carbonate cancels there, and you end up with what you need your final answer units of measure to be, which is grams of lithium carbonate. So we are going to multiply now 14.01 times 1 times 1 times 73.89 divided by 23.95 divided by 2 divided by 1, and that's going to equal 21.6. And we could go, it looks like, to 4 significant figures, so it's 29.61, 21.61. So I'm going to write it down here. So 21.61 grams of lithium carbonate. Okay. A couple more here. Okay, next question, D. How many liters of H2O are formed when 89.71 liters of CO2 are completely reacted? Alright, so we start with 89.71 liters, so that's up here at the top above CO2. And it wants to know how many liters of H2O, so that's the question mark. So it has 3 steps. We have to go from here into the equation, and then convert from moles to moles over there, and then come back out and figure out how many liters of H2O that is. Let's go ahead and set that up. Okay, so there we go. We have 3 conversions. Okay, first one is simply the standard 1 mole for 22.4 liters. So we're going to do that one. We need liters of CO2 to cancel out, so the 22.4 liters is going to have to be on the bottom. And the 1 mole is on the top. Alright, now we have to go, that puts us in the box right here under CO2. Now we have to go from moles of CO2 to moles of H2O. It's a 1-to-1 relationship. And we need moles of CO2 to cancel out, so we're going to put that on the bottom. Okay, and moles of CO2 cancels with moles of CO2, and I forgot to cancel liters of CO2 with liters of CO2. So we're right here. So we're now inside the moles box for H2O, and now we have to use the standard moles to liters conversion to get out to our final answer of liters of water. So moles of H2O has to go on the bottom. And 22.4 liters of H2O. Moles of H2O cancels and cancels, so you end up with liters of H2O. Okay, so it's going to be 89.71 times 1 times 1 times 22.4 divided by 22.4 times 1 times 1, and it gives you 89.71. What a surprise. Okay, or only 3 sig figs would be 89.7. So you end up with the same number. It's a 1-to-1 relationship between moles of carbon dioxide, moles of water in that equation, and so you end up with the same moles out. Okay. How many grams of lithium carbonate are formed if 52.6 liters of CO2 are completely reacted with lithium hydroxide? Okay, so let's go up, let's clean this up. Okay, so it's asking us for grams, how many grams of lithium carbonate. So, well, there's already a question mark there, that's what we want. Question mark there. Formed if 52.6 liters of CO2. Here's CO2, here's 52.6. Right there. So we have to start here, come into the equation to CO2, moles of CO2, come across to moles of lithium carbonate, and then come back out using molar mass to the grams of lithium carbonate. Alright, so let's go ahead and set that up. Okay, first conversion, we have to go from liters of carbon dioxide into moles of carbon dioxide using the conversion 1 mole equals 22.4 liters. So we can make 2 ratios. We need the liters of carbon dioxide on the bottom, so the 22.4 liters carbon dioxide on the bottom, 1 moles on the top. Liters carbon dioxide cancels and cancels. Now we're sitting in this box right here. We need to go from moles of CO2 to moles of lithium carbonate. It's a 1-to-1. And we need moles of CO2 to cancel out, so we're going to put that one on the bottom. And moles of lithium carbonate on the top. Moles of CO2 cancels and cancels. Finally, we need to go from moles of lithium carbonate. We're in this box right here. We need to come out using the molar mass to get grams of lithium carbonate. So we need moles of lithium carbonate to cancel, so we're going to put the mole part of that on the bottom. And the grams, which is 73.89, is going to go on the top. Okay, moles of lithium carbonate, moles of lithium carbonate. Grams is the last thing standing of lithium carbonate. So now you multiply everything through 52.6 times 1 times 1 times 73.89 divided by 22.4 divided by 1 divided by 1, and that's going to give you 173.5. And we'll round that to 176 because it's 3 significant figures down there. Okay, so that's how you do these. Hopefully these are you're starting to see the pattern that you use, the thought process that you use for these. By the end of next week, you want to be able to do one of these problems without drawing the graphic organizer and or the flowchart, either name. And okay, we're going to continue with this lesson with some additional problems and some review problems. Okay, as we get in a little deeper into this course, you're going to find that you're going to have to do some canceling of fractions. Now, the fractions aren't going to be numbers or variables. They're going to be units of measure usually. And so you have to know how to do that without actually doing the flip part of it when you have a fraction over a fraction. So this represents a fraction over another fraction, and we're going to give names to this. The top of a fraction, as you know, is called a numerator. But if you have a fraction on the top of a fraction, we'll call this the numerator top and the numerator bottom. Then you have another fraction down on the bottom, and that's called the denominator. That's the number on the bottom, or the thing on the bottom is the denominator. And if that's a fraction, we'll talk about denominator top and denominator bottom. So whether you can cancel units in any of these locations, there's just a simple rule. If you take these names and understand and learn these names, what those names are, any place you see a common name is a place where you could cancel a variable. So just take liters, for example, as a unit of measure that we may need to cancel. So numerator top can cancel. If there's liters there, you can cancel with liters in numerator bottom because they have the word numerator in common. Or you can cancel, if it's in numerator top, with denominator top because they have the word top in common. If you have a liter in numerator top and denominator bottom, you cannot cancel that because they don't have any words in common. Numerator top, denominator bottom, totally different words, so you could not make that cancellation. How about numerator bottom? That'll cancel with numerator top or with denominator bottom. As long as there's one word in common, you can cancel. How about denominator top? That could cancel with numerator top or with denominator bottom. And finally, denominator bottom can cancel with denominator top or numerator bottom. Okay, so let's go ahead and do this. So you're never going to get one this complicated, but this is just a nice little exercise to practice on. So let's start at the very top. So we have atmospheres. This is a numerator top. So atmospheres can cancel with numerator bottom. We don't see it there. Or denominator top. And we do see it there. So we're going to cancel atmospheres and atmospheres. Now let's go to liters. Liters could cancel with numerator bottom or with denominator top. And you do see liters in denominator top, so cancel those. And Kelvin. Kelvin can cancel with, Kelvin's in numerator top. It could cancel with numerator bottom. There is a Kelvin there, so we'll cancel that. Okay, let's go down to numerator bottom. Numerator bottom, we've taken care of numerator top, so we can skip past that. It can cancel with anything in denominator bottom. So the moles here can cancel with the moles here, and the grams here can cancel with the grams there. All right, and finally, we've taken care of everything in the numerator altogether. Everything, all 6 of them are gone. Now, how about grams here? Grams can cancel with grams down here, but there is no gram down there to cancel with. So what you're going to do then to write this as a final unit of measure is you have grams over atmosphere liters, but this is in the denominator fraction. So just like when you're doing fraction division, you flip the bottom. So you're going to end up with atmosphere liters over grams. These are the only units that are left, and that's what you would get. That would be your units of measure. Okay, try doing this one over here. So I didn't put parentheses around this, but I should. That makes it clear which is the, primary fraction, which are the numerator and denominator fractions. Okay, so let's start at numerator top. So grams can cancel if they're in numerator bottom, they're not, or if they're in denominator top, they're at 2. There's grams times grams, grams squared. So the way you usually do that is just scratch out the square, so that's not there anymore, and grams here. So you still have 1 unit of grams there. Okay, how about atmospheres? Atmospheres can cancel numerator top with numerator bottom, so let's cancel that. How about moles squared? Moles squared can cancel with moles in numerator bottom, so I'm just going to scratch out the square there. So that gets scratched out, and that's just the square gets scratched out. And that could also cancel with moles in denominator top. Top. There's no moles there, so it's going to stay. Kelvin. Kelvin can cancel with Kelvin in numerator top, numerator bottom. So same thing. I'll cancel this K, and I'll just cancel the square here. So you're just left with a single K there. All right. Now this K is in numerator bottom, so it can cancel with K in denominator bottom. So I'm going to cancel it. And then down here, this is K to the 4th. So I can cancel that and make it K. Why don't I just scratch the whole thing out? K to the 3rd. So you're left with K to the 3rd there. All right. So we've taken care of everything up here in the numerator fraction. Now we're going to come down. So liters can cancel with liters in denominator top with liters in denominator bottom. So this liter is going to cancel, and this liter is going to become L squared. So let me again just write it here as L squared, okay? And then you have atmospheres cubed and atmospheres squared. Well, those can cancel. And 2 of the 3 here, remember this is atmospheres times atmospheres, and this is atmospheres times atmospheres times atmospheres. So one of those remains. Both of these go away, and 2 of these go away to leave you with a single atmosphere there. Okay, so what do we have left? Let's circle what we have left. We have moles up here, nothing there. We have atmospheres here, and then we have liters squared and Kelvin squared. So you're going to flip the bottom. So for this fraction up here, you still have moles on the top. And then you're going to flip this bottom one here. So you're going to end up with liters squared, Kelvin to the 3rd. And then that's all going to be over atmospheres. This one right here. So this one flips down and goes onto the bottom. So this one flips. So this is this flipped, and then the mole was already there on the top. Okay? So that's how you would do those, all right? So these are way more complicated than any you're going to get, but in this next problem right above, you're going to see how this canceling works. Okay, so I want you to just show that 1 mole at standard temperature pressure is going to be 22.4 liters using the formula PV equals nRT. So let's go ahead and do that. So what does that mean? Let's line up our variables here. So 1 mole, that's N. Pressure is going to be standard temperature pressure, so that's going to be 1 atmosphere. Volume, volume is what we're going to find and see if it does equal 22.4. And temperature is going to be 0 degrees centigrade, which you add 0 plus 273 gives you 273 Kelvin. Okay. All right. So let's plug them in, and first of all let's solve for B. So PV equals nRT. Divide both sides by P. Cancel, and you have V equals nRT over P. All right, so let's come over here and write it out. V equals, N is 1 mole. R is, you don't have to memorize this, but eventually you will know it. 0.0821 liter atmospheres over moles Kelvin. And finally, you have T, which is 273. I left too close here. It's right there, 273 Kelvin. Okay, now you put that over P, and that's 1 atmosphere. So remember, if you only have one level, it's considered to be on the top. So this mole is on the numerator top. This atmosphere is in the denominator top. I could put a 1 underneath it like that, but I don't think we need to do that. So if there's only one level, it's on the top side of that fraction. So let's see how things cancel. Moles here cancels with moles there. That's in the numerator bottom, numerator top. Liters, let's do Kelvin. Kelvin is numerator top, and here it's numerator bottom. Atmosphere is numerator top and denominator top, so they cancel. And the only thing that you have left then is liters for volume, and that's what you measure volume in, is liters. So if you get on the calculator and multiply 1 times 0.0821 times 273 divided by 1, you'll get the volume will equal 22.4 liters. And you got to see how the units canceled out there as well. Okay, let's keep going. The chemical reaction in the previous page had an error in it, had a typo, so rather than correct it, I'm going to skip it. Let's just do one of these. So this is kind of routine, but we don't want to forget how to do this because it's critical to everything we're doing in the future, and just find molar mass. Okay, so let's just do a couple of them actually. All right, so MgOH2, and that's going to give you, so you just go ahead. Again, some of you can do these practically in your head, or you know how to organize them real quickly. So it has 1 magnesium, and magnesium is 24.31. So again, you get all these off the periodic table. Grams per mole. Oxygen, there's 2 of them. It's in parentheses, it's 2 of them, so that's 2 times 16. And hydrogen, there's 2 of those, times 1.01. So you just go ahead and set these up out here. And you add those. 58.33 grams per mole. Okay. This one, hydrogen, and phosphorus from the periodic table is 30.97. Okay, so you can add these up. And that gives us 98 exactly. Okay, and that's grams per mole. Alright, and MgO I'll leave you to do on your own. Alright, the last thing I ask you to do in this assignment is describe a covalent bond. So I'm going to say it to you. You can go back to the video. It's lesson 8 in the foundations, and you should be familiar with it. So a covalent bond is a bond formed between 2 nonmetals. Those would be the elements over in the upper right hand corner of the periodic table. Most of the bonds in your body are covalent bonds. And those are strong guys. They have high ionization energies, which means it takes a lot of energy to take an electron away from them. And they have high electronegativities, which means that they like to grab electrons from the outside, and they're very good at that. They're strong at pulling those in. So when two of those get together, it's like a tug of war between two strong guys on the electrons of the other. Neither one gives up its electrons easily. Both of them pull electrons very well, but neither one gives up electrons easily. So neither one can win the tug of war. So it's a tie, so they share the electrons. And if one of them is a little stronger than the other, and that's always true if they're two different elements, not like O2 where they're the same element, but if one is oxygen, one's hydrogen, the oxygen has a higher electronegativity than hydrogen, so it's going to pull a little harder on the electrons. It's going to pull the negative electrons over to the side of the oxygen. So the oxygen side of a water molecule tends to be a little more negative, and the hydrogen side tends to be a little more positive. And that's called a polar covalent bond. So that's how covalent bonds work. So go ahead and put that in writing. Go back and review the definition in Lesson 8 if you need to. Okay, that takes care of this lesson. Sorry if you spun your wheels and couldn't get anywhere on that balancing. It was a misprint and it wouldn't balance the way it was, so sorry about that. Okay, anyway, we'll get you on the next lesson, which will be Thursday's lesson, and it'll continue with gas laws and gas stoichiometry. Have a good day.